Let's start by asking the most basic question, what is a vector? And a vector is really just two pieces of information, direction and length, or what's also called magnitude. Two different words for the same thing. Now, length is a very physical, visual concept, right? It's something we can see, it's something we can measure. And the same with direction. It's our orientation. It's a very visual thing. So vectors, to begin with, most intuitively fit on a graph. They fit in a place where we can visualize them. And so how could we attempt to capture direction and length? Well, I think an arrow does a pretty good job. This, for instance, captures direction. It's moving in the northeast direction, and it also clearly has a certain length. And so this is a vector, and that's exactly how we graph vectors, just as arrows. This is also a vector. It's pointing in a certain direction. It has a certain length, as is this. So is this. This is a vector. Even though it doesn't start at the origin, it's clearly pointing in a certain direction, so it has direction, and it clearly also has length. So vectors need not start at the origin. They can start anywhere. This is also a vector. It's pointing in a certain direction, and it has a certain length. Okay? That's great. Now let's look at a specific example. Here is a vector, and I want to, first of all, name that vector. So I'm just going to call it V, and I'm going to put a little arrow over the top of it to make sure that we know that this is a vector. So the vector V, and now I want to capture this information. I want to capture the information that arrow is telling us without needing to draw it. So I can't, I'm not going to write this like this. I'm not going to say V is equal to this arrow. That's too ambiguous. I need something more definite, something with more structure. Well, this vector moves over a certain amount in the x direction. Let's say, for example, it moves over 3 in the x direction. It also moves a certain amount up in the y direction. Let's say, for example, it moves up 1. Well, now I can say that this vector is equal to its components. So that's a new word for us. It's equal to its x component, which is 3, how much it moves over in x, and its y component, which is 1, which is how much it moves up in y. So again, this is the x component and the y component. And now, anyone in the world looking at this vector, v equal to 3, 1, can go ahead and draw that vector if they want to. They know exactly which vector we're talking about when we write that. Just a bit of notation here. This is also written as a column. And it's the exact same information. It's just vertical now. And again, this is still the x component and still the y component. Okay, let's look at another example. Let's look at, let's say, the vector u. And let's say it has the components -2, 3. Well, that simply means we're moving over -2 in x and up 3 in y. So maybe something right around here. So this would be 3 in y and -2 in the x direction. And there's our vector. Nothing to it. And of course, we could have written this as a column vector, -2, 3, if we wanted to. Okay, so we have that down, but what about direction and length? Does this capture direction and length? These just using two components, how does that tell us direction and length? Well, it tells us direction because this is the vector that moves over 3 in x and up 1 in y. That's its direction, over 3, up 1. It points in that direction. But what about length? Well, that's what we're going to talk about in the next video, but I'll give you a clue. We've formed a right triangle here. The components tell us the length of the base and the length of the height of the triangle. And what we're trying to find is this length here, which is the hypotenuse of the right triangle. So maybe you know some formula or theorem that tells you how to find the length of the hypotenuse of a right triangle. And if you do, then you can figure out the length of this vector. And that's what we're going to do in the next video. See you then.